Okay, so this first one is a calculator question, and we'll definitely need a calculator for every part. So, okay, Diego runs back and forth along a straight track. During the time interval from t between 0 and 30 seconds, Diego's velocity in feet per second is modeled by the function v, given by v of t equals that function. Okay, what's the first time t1 that Diego changes direction? Find Diego's average velocity over the time interval from t between 0 and that same value t1. Okay. So we'll do two things. We'll first figure out the first time it changed the direction, so that's the first time that the velocity, which is this function, goes from either positive to negative or negative to positive. Okay, that'll usually happen over a zero. We'll find some zero of the function and then see the function like goes through the x-axis, crosses over the x-axis over some x-intercept. Okay, it doesn't have to be. The function could be undefined and go from positive to negative or negative to positive, and then that would represent a change of direction, but usually it's at an x-intercept. Okay, so this one will just graph this function, this velocity function, and just see when the first time is that it crosses the x-axis, basically. Okay, let's write that. So they say find his average velocity over the time interval. So average velocity is 10.504. Okay, and then let's give units just for practice. So feet per second. That's what this is, feet per second. And then even for this time, this is in seconds. Okay, for part B down below, they say at time t equals 30, how far is Diego from his position at time t equals 0? Okay, when they just want to know how far are you from a starting position, all that is displacement. And when you're doing displacement, you're just going to do, for us, we'll do integral from 0 to 30 of the velocity. Okay, this gives you how far he is from the starting position at t equals 0, how far he is from that starting position when t equals 30. Okay, so we'll look at the calculator again. Okay, so just go right to math 9, and we're just typing that in, 0 to 30. And then we've already got our function velocity function in y1, so we'll just go to y1, put that in there, and then dx. Okay, and that's it. So this will be in feet. This is a displacement and of position. That's feet. Okay, for part C, they say find the total distance that Diego runs during the last 30 seconds from t equals 0 to time t equals 30. Okay, whoops. Okay, so total distance traveled is integral from a to b of absolute value of velocity. Okay, and then that's all we'll do. So this will just be all in the calculator. We'll go from 0 to 30, and we'll do the absolute value of y1. To get absolute value, do math and then go over to the num tab. Their ABS is absolute value. And then just put y1 in there. Okay, and that's it. Okay. a little while sometimes when you're doing integral of absolute value. You see it's still thinking. And that's it. Okay, this is total distance, so this will be feet. Alright, last one, part D. So they said let A of t represent Diego's acceleration during the time interval from 0 to 30 seconds. Using correct units, explain the meaning of the integral from 5 to 10 of A of t dt in the context of this problem. Find the value of that integral also. Okay, let's find the value of the integral first. We'll do that by hand to a certain extent, and then find it in the calculator. So, okay, so think about when you're doing this integral, and just think about how do you evaluate an integral, or one way to evaluate an integral in general, using fundamental theorem of calculus. One of the parts, I forget which one, but to evaluate it, you find the antiderivative of this, and then you plug in the top and bottom limits into that function and subtract. So when you're finding antiderivative, you're finding a function that if you took derivative would give you back this function. Right? So what function when you take derivative gives you acceleration? And so that's velocity. So the integral of this is going to be velocity. And we'll evaluate it from 10 to 5. And all that really is v of 10, minus v of 5. Okay, so we'll find that in the calculator right now. Okay, and all this is just plugging in 10 and 5 into that function that's in y1, right? So we'll do y1 of 10, that's velocity of 10, minus y1 of 5, that's velocity of 5, and that'll be our answer. So really doing this by hand was the hard part. Once we did that, the calculator work, it was easy. 765. Okay, and then that is, this is velocity. These are differences in velocity, so this is feet per second. Okay, and then the last thing is to explain the meaning of this. And all this is the change in velocity over that time interval, how much it changed, really like the net change in velocity over the interval from t equals 10 to t equals 5. So we'll say on the interval from 5 to 10, Diego's net change in velocity, or of velocity, was 6.765 feet per second. Okay, something like that. Okay, so the first one for part B of the FRQs. So they say, first they give us some graph. They say let f be the function defined by f of x equals this piecewise function. So notice it's a different function between 0 and 1 and between 1 and 2. Okay. Then they say let R be the region in the first quadrant bounded by the graph of f and the x and y axes as shown above. Okay, so first thing is kind of weird that normally when you have a piecewise function it's not smooth like this. So the pieces go from 0 to 1 and then from 1 to 2, and usually there's a corner or cusp here, but it doesn't look like there's one, even though maybe there is. It's just really slight. But anyways, it looks like a continuous differentiable function even though it's piecewise, so not typical, I think. Okay, but that doesn't matter. So for us, they want us to first find R. Okay, the area is just taking the antiderivative. If there's a piecewise function, we'll have to take the antiderivative over each interval separately. Okay, so here I'll do area of R. Okay, so this will be the integral from 0 to 1 of the first piece. And this will be plus integral from 1 to 2 of the second piece. Okay, so I'm going to start back up over here. Okay, so so we'll just take antiderivatives and then plug in top and bottom limits. Okay, so antiderivative 2 is 2x. Antiderivative x squared is x cubed over 3, and we'll evaluate that from 1 to 0. Okay, the next one, we could actually integrate this, do u substitution. This is x minus 2 cubed over 3, and then we don't have to worry about a constant because the derivative of the inside is just 1. So I'm going to do this kind of quickly. Okay, you could also do u sub for this one. Okay, so here we don't have to bother plugging in 0. Technically we plug in 1 and 0 and subtract, but when you plug in 0, that'll be 0. So we'll just plug in 1, and we get 2 minus a third. Okay, we'll evaluate that in a second. And then for the next part, if we plug in 2, you get 0. Okay, so technically we're doing plus 0 minus, and then that, so but we don't need that. So, and then we plug in 1, and this becomes 1 minus 2, negative 1 cubed is negative 1 over 3 is negative 1/3. Okay, and then we can see here we have a minus 1/3, and this will be a positive 1/3, so those will cancel, and this ends up being 2. Okay, let's look if that makes sense. So then this whole area, let's say this is the way I would look at this. This is a rectangle, and the area of this rectangle is really a square. The area of this would be 4, and it looks like that's about half. Looks like this is about, could be half. We see it's, if our work is right, it's exactly half. So yeah, just to see that makes sense. Okay, so for part B, they say the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Okay, so our cross-sections are going perpendicular to the x-axis, so everything will be in terms of x. And then this will definitely be going from 0 to 2. That's the smallest and greatest x value associated with this region, or that bounds this region. Okay, they say write but do not evaluate an expression involving one or more integrals that gives you the volume of the solid. Okay, so we know with these types where they describe a cross section, we know we're going to go do an integral across that area of the base of the solid, and then technically we're just integrating an area of a cross section. Okay, so for us, if we look at this figure, so these are all squares, these cross sections. So then that'll be like the base of a square. It'll be coming out of the paper. Certain amount. And then this will be the square. Okay, so notice, this is a square, so first off, just to show, I'll show work. This is really side length squared. So we really just need to get what this side length is in terms of x. So this side length is just the distance from the function down to the x-axis, which just is that function. So this distance is really just the value of the function. The y value at this point is the same as this distance. And so that's all we're going to plug in. Is just plug in this function. So here. So the fact that this has two different functions though means that we'll have to split it up. So we'll do one from 0 to 1, and we will just square this first one, square that first function. Okay, so that'll be the volume of the first one. And then we'll do integral from 1 to 2. And remember, we don't have to evaluate this. We're just setting it up. And then square the second function. So when you're squaring it, it's just going to multiply the exponents. So this will become x minus 2 to the 4th when you're squaring this. Okay, and that's it. Yeah, so we were doing side length squared. Side length was the function, so we had to square that, but we had to use each different function for the different intervals from 0 to 1 or 1 to 2. Okay, part C, they say the portion of the region R between 1 and 2 is revolved around the y-axis to form a solid. Find the volume of the solid. Okay, so now they're not talking about the whole thing. They're just talking about when x is between 1 and 2. And they're talking about this region here. This region here. So that's the region that's getting revolved around the y-axis. Okay, so if it's getting revolved around the y-axis, so there's a few things to think about. First off, we're only dealing with this function here. It's almost like this function doesn't exist and doesn't even matter because yeah, this function is not coming into play for us. So yeah, so only worried about this bottom function, x minus 2 squared. This is being revolved around the y-axis, so everything has to be in terms of y. So we'll have to get this function in terms of y. And then the other thing is when we're finding the radius, so this will be like a radius, find the volume of the solid revolved around. Oh, okay. Oh, here. So we're taking this portion. So when we revolve this around the y-axis, let's do this just to remind us. Oops. So revolving around the y-axis. When we revolve this around the y-axis, there will be this hollowed out part. So that lets us know that there's going to be two different integrals. And actually, technically, I don't know, we could do it different ways. If you notice, when this gets rotated around the y-axis, this area, the hollowed out part happens to be a cylinder, or will be a cylinder. So we could actually just use volume of a cylinder formula and subtract it. But anyway, we'll do it kind of a normal way. Okay. So first thing is, we'll do the outer radius. It's just the value of the function. But we have to get it in terms of y, so let's do that up here. So first we have y equals 2 squared. Okay, we can square root both sides. Okay. And then when you square root a square, we'll still have absolute value, like that. Okay, I'm going to switch these around just to solving for x. Let's put that on the left. Okay. All right, now you just have to think about it. So we're plugging in a value between 1 and 2 into here, and but it's absolute value. So tell me if this makes sense, that we can actually just do x minus 2. So think about it, if we plug in a value, if this x can only be a value between 1 and 2, that means this will always be negative, or 0 if x equals 2. And so this absolute value will always make it positive. But to get rid of absolute value, the main thing is we just want to make sure that this is always positive, just like absolute value would. And so we can put a little negative on the outside to make it positive, just like absolute value would. And so we have that. Alright, so now we can solve for x. I'll negate both sides and add 2. So it'll be negative root y plus 2 on the outside. Alright, so that'll be the function that we use in our integrals. Okay, so now we're doing the integral from 0 to 1. Remember, these are y values. We're revolving this area, and this area goes from 0 to 1. So that's 1. We could, if you plug in 1 in here, you get 1, so that this point's 1 comma 1. So this goes from 0 to 1. Okay, and then we're doing a volume of revolution. So we're doing a pi times r squared. R is this distance, which just is this function, but in terms of y. So this is what we're squaring. I'm going to write that as 2 minus root y, same thing. Okay, so that's it, pi r squared. Okay, and then now we want to minus the hollowed out region, and the radius of the other part is just from here to here, and that distance is always 1, no matter what. No matter, it doesn't matter if you pick here to here, here to here, here to here, that's always 1. So all we're really, this function is just the function x equals 1. So technically we're doing pi times 1 squared dy, but that's really just 1. So okay, so I'm going to pull out the pi and just make it all one integral. The integral from 0 to 1. Okay, so in order to eventually solve this, we'll have to square this out. So squaring a binomial, I'm going to do it quickly. This will be y minus 4 root y, and this will be plus 4. When you square this out, you'll get a plus 4, 2 squared, but then we'll be minusing a 1, so this will really just be plus 3, like that. Okay, so now we got to integrate that. So let's do that here. Okay, one thing, this is, here we have a y, so the integral of y is just y squared over 2. Okay, this is really a y to the 1/2, so this will be y to the 3/2 times 2/3, and then times it by 4, this will be 8/3, y to the 3/2, and then the integral of 3 is just 3y. Okay, zeros don't matter, so we'll just be plugging in 1. So this will be pi times 1/2 minus 8/3 plus 3. Okay, common denominator is 6, so this will be pi times, so 3 minus 8 plus 18. Okay, these are all just the numerators of these fractions if you got them over 6. So if you over 6. This would be 3 over 6. Oh, this should be 16. I don't know why I did that. Yeah, so this would be 16 over 6, and this will be 18 over 6. Okay. And then that all simplifies to be 5 over 6. So that'll be 5 pi over 6. Alright, and that's it. Okay, and the answer key in College Board is wrong. So they didn't have this as a negative root y. They had this as a positive root y, but that's not correct. And just to see clearly why, so think about this function should be the same as this function when x is between 1 and 2. So if you think about it, let's say when x is 1, here, when x is 1, this is 1 minus 2, negative 1 squared is 1, so when x is 1, y is 1. But here, when y is 1, square root of y, that's 1, negative 1 plus 2 is 1, so that works. If this negative wasn't there, then when y was 1, this x would be 3, and that's not right. Yeah, so the answer key is wrong. They didn't include this negative like you need to include. So this is the right answer. They had 37 pi over 6 because they had this as positive, but that shouldn't be positive. That should be negative. So okay, so number 2 from part B of the FRQs. They say let R be the region bounded by the graph of y equals 3 parentheses x minus 1 over root x, the x-axis, and the vertical line x equals 4. Okay, so this is that function that they have. Here's the x-axis, and here's the vertical line x equals 4, so that region is bounded by those 3 lines. Okay, first find the area. Okay, so we know at least setting this up, we're going to do integral from 1 to 4, because that's where the area goes to and from. And then we're just going to integrate this function. Okay, so that'll be the area. So basically we just really have to integrate this function. So let's rewrite this. So first off, we can distribute the 3 to the top. And then I'll change that root x to x to the 1/2. And then our method for finding the antiderivative of this is splitting up this integrand. So we'll do 3x over x to the 1/2 minus 3 over x to the 1/2. And when you do that, you get 3x to the 1/2 minus 3x to the negative 1/2. Okay, so that's the thing that we really have to integrate. Okay, integral of x to the 1/2 is 2/3 x to the 3/2, and the 2/3 and the 3 will cancel out to be a 2. And just check your work. You can see if you took the derivative of this 3/2 we get multiplied by this to be a 3, like you want, and then you'd subtract 1 from this to get the exponent like you want. Okay, and then we'll do minus, or maybe plus, let's see. So for this, when we integrate, we'll add 1 to this exponent, that'll become a positive 1/2, and then times by the reciprocal, which is 2. So this will be minus 6x to the 1/2. Okay, so just a little algebra, and you can check again. If you take derivative of this, you should get this. Okay, so let's plug all these in. So plug in 4, you get 2 times 4 to the 3/2. 6 times 1. Oops. 6 so plugged in 4, and then minus plug in 1. Okay, and then when you're evaluating a number to a fractional exponent, you can do either one first, but the bottom of the exponent is the root and the top is the power. So if the root goes in evenly, or if you can take whatever this root is, if you can actually take it of this number without a calculator, then you should do that. So this 2 represents a square root. Square root of 4 is 2, and then this 3 is the power. So 2 to the 3rd is 8 times 2 is 16. Then here this is just square root of 4, which is 2 times 6 is 12, and then minus. And then these exponents don't matter, so this is just 2 minus 6, which is negative 4. Okay, and then that's really 4 plus 4, and that's 8. Okay, the last part they say, find the volume of the solid generated when R is revolved around the x-axis. Okay, so revolving around the x-axis, so everything's going to be in terms of x. We're going to have a pi r squared in our integral. And the r, so this is the radius that we're revolving around the x-axis. I'll draw a little line like that. So keep in mind, this is just one of the cross sections. This is a circle. That's just one of the cross sections. Technically you'll do that for every one of these radiuses, so this will be some big circle. Okay, and technically you do that and it forms some kind of, I don't know, like a little sand dune sideways or something. Okay, so find the volume. So we know we're doing it in terms of x. So this goes x-wise, this region goes from 1 to 4, so those will be our limits. And then we know we're doing some pi r squared dx. Okay, the radius of all these cross sections, or technically we're finding the area, which is the pi r squared part. And then the area of this cross section, the only thing we really need is the radius, and the radius just is the function. So the radius is like that. Okay, and then that's our function, and we just have to square it now. Okay, so now I'm going to, let's write this. So first I'm going to square all these things. So I'll square the 3 first, so that'll be 9, and I'm going to pull that out, so that'll be a 9 pi on the outside. And then we're going to square top and bottom here, so that when we square this root x in the bottom, that'll just become an x. And then when we square x minus 1, we'll get x squared minus 2x plus 1. And so we're just going to be dividing this by x, which is root x squared. Okay, so when we do that, so then we'll go from 1 to 4. So divide those by root x, or divide those by x. So x squared divided by x is just x. And then negative 2x divided by x is just minus 2. And then 1 divided by x we'll just leave as that. Alright, so now we can integrate. This will be x squared over 2. This will be 2x, and this will be ln x. And technically it's ln absolute value of x, but we're going to be plugging in positive numbers, so it doesn't matter. I'll write absolute value just but just so we know it doesn't matter for this particular problem. Okay, so 9 pi. Okay, plug in 4. So 4 squared is 16 over 2 is 8. And then negative 2 times 4 is negative 8 minus 8. And then plus, so you get ln 8. Minus, and let's plug in 1. So you get a 1/2 minus 2. And then technically this will be plus ln 1, but ln 1 is 0, so we don't need that. Okay, and then we'll simplify this. So these 8's cancel, and then this is really just a minus negative 3/2, which is plus 3/2. So we could write this as 9 pi times 3/2 plus ln 8. Oh, and I just noticed a mistake that y'all might have noticed. I don't know why I did this. Maybe because these were 8's, I put an ln 8. But when you plug this ln 8, this should have been ln 4, because that's what you get when you plug in 4. So I'm going to change that to an ln 4, which will just make that an ln 4. Okay, let me fix this. Alright, and then that's the answer. And that's probably the most simplified that you'll want to go.